So, we're going to talk about the relationship of Newton's second law, momentum and impulse. And actually, in 1687, when Newton published his The Mathematical Principles of Natural Philosophy paper, the way he originally had the second law written, so what we understand the second law to be is force equals mass times acceleration. But the way Newton originally had it written was that force is equal to the change in momentum over the change in time. So we're going to talk about momentum and how it relates to Newton's second law and this new concept, impulse. Momentum, we use the letter P to represent it mathematically, is an object's mass times their velocity. And generally speaking, when we're representing a situation, we consider the idea of conservation of momentum, which is based off of Newton's second law, and that we really look at it in relation to specifically collisions. So I want you to think either two cars crashing together or two billiard balls hitting each other, right? Pool table balls. Before and after, they have momentum, and the amount that they have before is equal to the amount that they have after. If it isn't, we account for it somewhere, right? Either went to friction, and how does friction take energy or momentum from a system? It transfers it into thermal energy, heat, which is why when you rub your hands together, they get warm. So it goes somewhere. So momentum is conserved in a system. And this idea of change in momentum is that I have the change in the mass and the velocity of a system. And that change in anything is always the final minus the initial. So that's going to equal the mass and the velocity final minus the mass and the velocity initial. And unless we're talking about like a rocket propulsion where it's burning fuel as it leaves the atmosphere, so its mass is changing over time, mass is generally considered to be constant. So for every example we're going to look at, we're going to set mass to be constant. And we can actually pull it out of this. It's kind of a semi-derivative here, but we can pull it out of that because it's just a constant. And that gives us that the mass is equal to the final velocity minus the initial velocity, which again is just the change in the velocity. So we can, sorry, not equal, my bad. Times is just then going to be equal to the mass times the change in the velocity of a system. So that being said, then all of that is over dt. So we're going to rewrite Newton's second law. So he had it as force is equal to change in momentum over change in time. That is now we know mass times the change in the velocity over the change in time. But what is the change in velocity over the change in time? That is just acceleration. That's the mass times the acceleration. So that's where we get what we standardly know as F equals ma. It comes from that change in momentum relation. The other thing I want to talk about is impulse, this idea of impulse. We represent with the letter I. It is equal to the change in momentum. So this is, again, we've denoted it as the mass, the change in the velocity of a system. We can kind of write it like that. The other equation you will see a lot, though, is how impulse relates to force. If impulse is the change in momentum, then Newton's second law, force is the change in impulse over the change in, or the change in momentum over the change in time, can be rewritten as force is equal to the impulse over the change in time. And we can relate impulse for this as that the impulse is equal to the force times the change in time, which is probably one of the forms that it's used in the most, is how it can relate to force. And I want us to think about the example, say my friend's car is stalled and we need to push his car to the gas station. Maybe it ran out of gas, right? And we're going to push it to the gas station. The longer I apply a force to the car over the longer period of time, right, the more impulse or change of momentum it's going to have, right? So this can be directly related, remembering that this is the mass, the change in the velocity, that's equal to the force, the change in the time. The longer I apply that force to the car, the more its impulse, the more its impulses, the more its impulses, the more its momentum changes. So and in this direct relationship to me pushing on my friend's car, if the faster it would go, right? Why in real life doesn't it go faster? Friction, right? There's a ton of friction, not just between the tire and the roads, but also the rotators in the tire, um, and the rotators in the car and the wheels. There's a lot of varying parts going on there that make it so it doesn't exactly crazy speed up, but it also does get easier to push as it keeps going. And that all actually has to relate to this concept and this idea of impulse. So let's look at just an actual really simple example of the billiard ball scenario, where I have two billiard balls. We'll call this ball A and this ball B, and they're coming together from opposite directions. So let's say A is approaching at a velocity of, we'll say, 2 meters per second, and B is approaching at, we'll say, a velocity of 1 meter per second. Okay. And because they're billiard balls, they're really set to be of equal mass. I have no idea what the mass of billiard balls is, but let's assume their mass is maybe a realistic mass of 0.05 kilograms, maybe. That might be a little heavy, but we'll go with it. The idea should be the same no matter what their masses are. Before the collision, I can represent, so I can write the before the collision as the momentum is the sum of the individual parts. So it's going to be the momentum of A. So I can P of A plus P of B. And that's going to equal what it is after. And for billiard balls, they're a good example of this. Brings us to the idea of types of collisions. There's two types of collisions. There's elastic and there is inelastic. An elastic collision is where they don't stick together. When you think of the billiard balls example, they're going to bounce and then they're going to go their separate ways. The nature of the thing, the way it's built, and the substance of it has to deal with how much it's going to be elastic or inelastic. Well, in real life, there really isn't an example of a perfect elastic collision, right? In real life, energy gets lost somewhat on impact, right? But the idea is to get as close to it as possible. Billiard balls can approximate a perfectly elastic collision. Inelastic collisions would be an example of a car crash. Cars are actually built to kind of crumple a little bit on the outside. Airbags help to take some of that momentum away so you don't feel the force so much. If I think about the more my momentum changes, the more my impulse goes up. If my impulse goes up and the change of time is short, then my force has to increase exponentially. And a huge amount of force on a person could kill them, right? So cars are actually designed in ways to lessen the impact, right? So the impact or the force over the time, right? So they extend by essentially extending the time period. They can lower that impulse. Now, the after the collision for the billiard balls example, the billiard balls example again would be approximating a perfectly elastic collision. Their after momentum, since they're not going to stick together, is going to be the sum of their individual parts. So it's going to be the momentum of A plus the momentum of B. So let's compare it to a car collision. So we say we have two cars and they are driving on the road. Before they collide, right? And this, it is important to note so the two examples I'm talking about thus far are in they're in the same direction to each other. Now, momentum is a vector because it has velocity in there. It is a vector. So it does matter the direction in which the objects collide. But in the case of the cars, before they collide is going to be a momentum of their individual parts. We call this car A and this car B is going to be P of A plus P of B, and that's going to equal their momentum after. In the case of the cars, this is a relatively inelastic collision. In some cases, they can bounce off each other. You've probably seen that happen. But for this example, let's say the cars collide and they stick together and start sliding together. That would be an inelastic collision. That means we have to consider the momentum of the after situation as the momentum of their now system, the system of the cars. So we can call it P of the system. which is going to be the combination of their mass and whatever velocity ends up after. And we'll look at some actual examples a little later on.